Hey everybody, welcome back. We're going to be looking at activity 33 today, mostly lesson 33-1 in your textbooks. Sine, cosine, and tangent of unknown angles, and sometimes known angles, without a calculator, maybe a little bit of a calculator to do some of the squaring or square rooting that we're going to have to do, but no decimals. And so the unit circle is a nice reference piece here, but not necessarily necessary here. We just want to kind of go back to what this idea of sine, cosine, and tangent ratios are. So this lesson could be titled a lot of things. The book talks about it being the Pythagorean identity, but I think the title right above it, more than just triangles, is really big because we're bringing back this idea of triangles when we've been working in a circle. So is it circleometry or triangleometry or trigonometry? Trigonometry. So how do we look at those things? So there is this Pythagorean relationship because we're mixing together this idea of circles and triangles. And so we know we've used the Pythagorean theorem already for our special right triangles to find all three sides and kind of understand those. And then we enhance this on Tuesday talking about the tangent ratio. So sine, cosine, tangent. We understand tangent is sine divided by cosine. That's a really big idea that we're working with here. You know, sine divided by cosine is that tangent piece. But the other piece we've really looked at a lot in geometry class in particular was SOHCAHTOA, right? This idea that the sine of an angle is the ratio of the opposite side of the triangle and the hypotenuse of that, again, right triangle only that we're looking at. Pythagorean theorem only applies to right triangles. But then we started expanding that, okay? And then cosine was adjacent over hypotenuse and tangent was opposite over adjacent. So that's what we start with, and the Pythagorean theorem and being able to look at these things. Well, now let's apply the Pythagorean theorem to what we're looking at in our unit circle. Our unit circle always has a hypotenuse of 1. So from the Pythagorean theorem, it says leg squared plus leg squared equals hypotenuse squared. X is one of my legs. Y is the other leg. So x squared plus y squared equals 1 squared, or x squared plus y squared equals 1, which if we replace it then, and you'll see this on the next page of your textbook, sine of theta, all being squared, plus the cosine of theta, all being squared, is also going to equal 1, because the sine theta is our y. I kind of wrote this in a different order, y squared plus x squared, but our sine is y and our x is cosine, so y squared plus x squared equals 1. Therefore, sine squared, and again, we can notation-wise write that as sine squared theta. That does not mean sine of theta. That means sine of theta times sine of theta. Two separate fractions or ratios multiplied together. Cosine squared of theta, just some notation stuff there, equals 1. So sine squared plus cosine squared equals 1. This gives us an equation where if we knew sine, we could figure out cosine. If we know cosine, we can figure out sine. And we'll see that on the next page as well. Okay, so typed out, here you see what we just explained to you before, that you have this idea of the Pythagorean identity, which you could add to your word wall, that sine squared theta plus cosine squared theta equals 1. It winds up being super useful. I'm going to show you how the book attacks problems using this, like given some information, how can we figure out the other pieces, and then I'll show you an alternate method of solving as well, whichever one you like, the book method, which we'll go through first, or my method, which we'll go through second. You can use either one on the homework as you try to make sense of this. So let's take a look at example A. They're going to give us some information. They're going to give us that the cosine of an angle. Now notice, we don't know what this is. It may not be 30 degrees or 60 degrees. It may be something bigger. In fact, we know it's between pi over 2 and pi. So it's between 90 and 180. It's over in quadrant 2. And it wants us to find the other trig values. We don't know what theta is. Could be 95, could be 117. We don't know, and we don't need to know. We're not using our calculator here. We could do inverse trig like we did in geometry, but that'll be something we pick back up in pre-calculus. So using what we just talked about, this Pythagorean identity, we know sine squared plus cosine squared equals 1. The book says, oh, well, I know what cosine theta is. It's negative 3/5. So sine squared plus that negative 3/5 being squared equals 1. Negative 3/5 becomes 9/25. I can subtract 9/25 from both sides. That gives me, this is 25 over 25. So 25 minus 9 is 16/25. I can take the square root of both sides. They forgot here that it should really be plus or minus square root of 16/25, and then it's plus or minus 4/5. And then they realize, hey, this thing up here told me I'm over in quadrant 2. In quadrant 2, this is negative x, positive y, right? My sign is going to be the positive version, so that's why sine of theta must equal that positive 4/5. So they made that determination because they know what quadrant it's in. And then, of course, using tangent, tangent, of course, is sine divided by cosine. So 4/5 divided by negative 3/5. If we write it out the long way, 4/5 divided by negative 3/5, 4/5 times negative 5/3. The 5's divide out, and you get negative 4/3 like you see here for the tangent. So again, much like we solved for tangent in yesterday's example. So just, again, using a very simple Pythagorean style approach to it. We'll do one more like that, and then from there, I want to show you a different method to how you might attack these problems. Again, we don't even know what theta is. We just know approximately what quadrant it is in. So let's take a look here at the try these A and B on the next page. Okay, so I'm going to do the A style, like the book, and then the B style, I'm going to show you a new method to attack it as well. So for this one, it gives me the cosine. So again, if I'm thinking about sine squared theta plus cosine squared theta equals 1, I don't know sine, so sine squared theta equals, plus negative 8/17 equals 1. And negative 8/17 squared, I'm sorry. And so this is, again, a little bit where maybe just a 4-function calculator can help. Sine squared plus, that winds up being 64/17 squared, which again is going to be 289 equals 1. I can subtract that from both sides, so minus 64/289, minus 64/289. And then sine squared of theta equals, well, that's going to be 289/289. So 289 minus 64 is 225/289. I can then take the square root of both sides. Remember, when we take the square root ourselves, it's plus or minus 225/289. And most of these will work out to be nice square roots. So the sine of theta is either the positive square root of 225, which I believe is 15/17, so plus or minus that. Let's take a look up here. This is quadrant 2. So therefore the sine is positive. So it's going to be the positive 15/17 for the sine of theta. And then the tangent of theta is going to be sine divided by cosine. So 15/17 divided by negative 8/17. 15/17 times 17/-8. 17's divide out. The tangent of theta, again, we don't know what theta is, equals negative 15/8. Okay, so that's using the Pythagorean identity. Sine squared plus cosine squared equals 1. I'm going to show you a little bit different. It's still going to use the Pythagorean theorem, but kind of looking at that as well. So part B, different style. This is Mr. Rohde's preferred style. You might like it better. So we're given the cosine of the angle, and we're given that this angle is in between pi and 3pi/2, so that's quadrant 3. If I draw a quick sketch here of where this angle could be, I know this angle is over here in quadrant 3. Okay, so I just want you to start there. That angle's over there in quadrant 3. It could be on the unit circle or it could be beyond the unit circle. And I'm actually going to use this idea of SOHCAHTOA again that we've seen in geometry that you might like a little bit better. So the cosine is the A over the h. My adjacent side is going to be my negative 5, or it could be positive 5, but because I'm going left, it's my negative 5. The hypotenuse is positive. It has to be. It's 13. It's just a length. And then this length over here, my opposite value, my y value, right? What is that? Well, remember, this is a right triangle, and this might make your Pythagorean theorem actually a little bit easier, where you could say, oh, well, that's just negative 5 squared plus y squared equals 13 squared. So 25 plus y squared equals 169, y squared equals 144, y equals plus or minus 12 when I take the square root. The y is going down, so therefore it's the negative 12 version, okay, not the positive 12 because of what quadrant I'm in. And so the sine of theta is opposite over hypotenuse. What's my opposite? Negative 12. What's my hypotenuse? 13. Negative 12 over 13. And then here, what's my tangent of theta? My tangent of theta is TOA, OA, opposite over adjacent. My opposite is negative 12. My adjacent is negative 5. So my tangent of theta equals positive 12 fifths. Now, I think that goes a little bit quicker than the way the book does it, and it's still based off of that Pythagorean theorem idea. So I'll do a couple more like that to help you kind of sink these in. And again, you'll have a good chance to practice with these on the homework as well. All right, take a deep breath, pause if you need to, come back and let's look at this. Check your understanding number 1 and number 2, and then we'll go from there. Or pause, try it yourself, and then compare your answers to mine. That's really the best way to do it, is try to do it on some scratch paper and then come back and see the answers. Okay. So I'll go ahead and draw this out live. I've got an angle. It's in quadrant 1. Okay, don't know how big it is, but I know it's in quadrant 1. And if I'm looking at that theta, this is the adjacent over the hypotenuse from that SOHCAHTOA that we learned in geometry. So the adjacent side is 7, and that's a positive 7 because it's going to the right. And the hypotenuse is 25. This must be my y value. So I get 7 squared plus y squared equals 25 squared. 49 plus y squared equals 625. Y squared, 576. If I take the square root, plus or minus the square root of 576. And that might be a little bit tougher, but I know you guys can use your calculators to figure that out. That winds up being 24. If you learned your Pythagorean triples back in the day, this can be really helpful. So plus or minus 24. Obviously, this is going up on the y, so this is positive 24. And so now, really, we already have cosine, so it wants the sine of theta is O over h, opposite is 24, hypotenuse is 25. And then the tangent of theta equals O over A, so opposite 24, adjacent 7, tangent of theta equals 24 over 7. All right, and last example on this page, I think we'll do one more after this because it'll be a nice little piece here. You'll always work with Pythagorean theorems, stuff that should work out to whole numbers for the most part, unless it's like the last problem. So we'll see that. So let's take a look at this one. What quadrant I am? I'm in quadrant 2 because I'm between essentially 90 and 180. So I'm somewhere over here. That means my cosine will be negative and my sine will be positive. So my sine is 3/5. So O over H from SOHCAHTOA. So in that case, my opposite side is 3, my hypotenuse is 5. And again, we're making this bigger than the unit circle. Even though it would pass through the unit circle, all the ratios stay consistent. And so then this x value is what I'm looking for. Now this Pythagorean theorem I like. X squared plus 3 squared equals 5 squared. Pretty simple to solve. 3, 4, 5 is the Pythagorean triple if you just happen to remember it. X squared equals 16, so x equals plus or minus 4. Obviously, in this case, it's going to be the negative version, negative 4. So therefore, the cosine of theta is what I'm looking for, is adjacent over hypotenuse and negative 4 over 5. Again, we don't know what theta is here. It could be 95 degrees. It could be 127 degrees. That's something we can figure out with a calculator, but for right now, we're just kind of leaving theta unknown and finding the trig ratios that are associated with it. And the tangent theta, the OA, opposite over adjacent, 3 over negative 4. Tangent theta is negative 3/4. Okay, and here's our very last example for this lecture video. it gives us this crazy thing for the sine value, and then it tells us it's in quadrant 2. So some of you might realize what's going on already here, but let's just investigate this a little bit. If I'm in quadrant 2, and wait a second, the sine of theta, this reduces. It's a weird way that, like 2 divided by 4, that's 1 over 2. So this is the sine of theta equals root 3 over 2. Wait a second. My sine is root 3 over 2. So this is root 3 over 2. That looks familiar. I know that's got to be something for my unit circle, right? So if this is 1, right, then my x-coordinate must be a 1/2, and it must be a negative 1/2. I can even think about where this is in my unit circle. Wait a second, I know that I actually know theta just because they happen to give me a nice value. So I don't even have to go through the Pythagorean theorem because this would all work out the way we saw in the special right triangles piece. So if you ever see something weird like this with those root 3s or root 2s, it probably is one of our common angles on the unit circle. So in this case, if I look at my unit circle, that's going to be at 120 degrees, or also known as 2 pi over 3 here. So theta equals 2 pi over 3. And again, just we know some of these values already. Cosine of theta is going to be negative 1/2. And then the tangent of theta, sine divided by cosine here. So that is root 3 over 2 divided by negative 1/2, which becomes root 3 over 2 times negative 2 over 1, negative root 3. So I get tangent of theta equals negative root 3 on that particular one. So again, sometimes it looks like the theta is unknown, but in reality, it's one of the common angles we've been dealing with from back on Tuesday. All right, so good luck on the homework. I got one more thing to show you with the word wall, and we should be good. Okay, if you've been keeping track of a word wall or just notes in your own notebook to help you here, here's that again, so you can pause and make sure you get caught up. But the big things from today that I would recommend having down there are some of the identities that we've gone through here. So what do those identities really look like? Well, we saw one on Tuesday, that the tangent of theta was equal to sine of theta over cosine of theta, or also kind of that y over x on our unit circle, right? We also saw that the sine squared of theta plus the cosine squared of theta equals 1. That's something called our Pythagorean identity, which we'll use a lot more in pre-calculus. And we still use this idea of the SOHCAHTOA to help us kind of figure out those ratios again. So sometimes you have to decide which rule makes the most sense, which concept is going to help you get there. And there's more than one way to get there. So if you know that these particular things are true, which one is the most helpful? Some might be easier, some might be harder, but starting with them can help get you to the right place as you kind of go through this. So there's the Pythagorean identity and SOHCAHTOA. Lesson 33-2 is going to be a little bit more enrichment this year since we're going through distance learning. So I'll post some videos today as well as on Tuesday for you to look at just for enrichment purposes. But especially if you're taking honors next year, definitely want to watch those secant, cosecant, and cotangent. There are 3 more trig functions on top of sine, cosine, and tangent, but they're just the reciprocals of what we've been dealing with. So again, reach out to me via email if you need help or visit the Zoom sessions. And again, we'll plan on having an assessment next Tuesday, May 5th.